So, got my safety specs on this one because it's all about safety. This contraption is a vacuum chamber. So, just before I turn it on, I just want to show you the little demo, so I'll bring the camera closer for that. I just want to talk about something very simple, but it's not often thought about. Why is it quite easy for me to lift this off this surface? Because I've created a sealed container with air on the inside, and then there's all the air on the outside. And the reason this is easy for me to lift off is because the pressure is balanced. Okay, I've got air inside here, which I've collected in, and what that is doing is running around on the inside, hitting the walls of the container, transferring, a force, pushing outwards, and that creates an air pressure. And the air pressure on the inside of this is 100,000 pascals. The air pressure on the outside is exactly the same, 100,000 pascals. There is no difference in pressure. And what that means is that if I want to lift it up, I'm just creating a net force. I'm able to overcome this because the two air pressures are exactly the same. Now, a guy called I forget who it is, but he did this demonstration in Magdeburg. It's called a Magdeburg sphere. It's a similar idea, which is, well, what happens when you suck the air out of this? So you remove the pressure on the inside that's helping to push out. Well, if you do that, you end up with this scenario. Now, I just want to show you once again. Lift that up, comes off quite easily. If I turn this on, I start sucking the air out the inside. You can't see anything because air's just disappearing. Turn it off, if I'm trying to lift it up. Well, that is now held there. Because now what's happening is that the air pressure, there is no from the inside, there's no push outwards. There's no pressure on the outwards trying to push out. The reason this thing isn't collapsing in on itself is because it's very strong. It's designed to withstand that difference in pressure. But now there is basically a net force inwards. And actually, it's really hard for me to overcome it. Okay, in actual fact, because I never really encounter 100,000 Pascal pressure difference. It's probably not quite that good at the moment. So it turns out that that's really difficult. Okay, so you might just think I'm incredibly weak. So never mind. In order to be able to lift it up, I need to balance the air pressure. How do I do that? Make a hole in it. Now that sound wasn't air rushing out; it's air rushing in. And now, perfectly easy to lift this up. So that's the situation we're going to create on the inside. And what we're going to do is show you a few little demonstrations of what happens when you put things into this kind of scenario. So I'll bring the camera a bit closer. So let's start with the humble balloon, okay? Not made it very big, have I? So a balloon is a trapped vessel of gas. So inside it, and the balloon is the shape it is, much like this, because there's air on the inside pushing out, making the balloon stretch. But there's air on the outside that's pushing in. So, this is a balance of the pressure and the volume. So what I'm going to do is I'm going to put the balloon inside and turn it on. And so what we've got to create is a situation here where we're going to suck the air out of this tube, but we can't remove the air from the balloon because it's tied up inside it. So we're going to end up with a column that is empty of air, and inside it is going to be a vessel with air in it that is quite stretchy. So, make a prediction. What do you think is going to happen? Well, let's find out. This is so cool. So, I'm going to bring this version. This balloon, obviously, it's increased in size. It's also formed a really weird shape around it as it's in there. So it's forming the shape. And eventually what you could do is you could keep going. Eventually it might get big enough to burst and then the air would get sucked out. But that's the weird shape that the balloon makes. Now, why does that happen? Well, we have a gap where we have this air, this space around it where we're removing the air, so we're reducing the air pressure. So now we've kind of got the opposite problem where the pressure on the inside of that container is greater than the pressure on the outside of the container in terms of the balloon being the container. And so it takes up more volume. And if we want to equalize it again, going to let the air back in. So we're going to hear the rush of air going back in. And what do we get? Balloon goes back to its original size. And that is the first of our little, quite cool demonstrations. And it feels a little bit warm because of the work that's been done in stretching and shrinking it a little bit. And there we go. That's our first demo. What you're seeing in front of you is a beaker of water. It's recently come out of the kettle, but it is not in and of itself boiling. In fact, what I'll do is I will show you that it's just recently come out of the kettle, because there's my kettle, there's some water going into it. I wouldn't boil something that's not water in my kettle. And we're going to get a measurement of its temperature. So it is around about, yeah, it's a bit over, it's climbing over 70 degrees. And so, what am I at? About 75 degrees with this. So there you go. Now see it going. So it was over 70 degrees. I'm going to ask a question of what is boiling point? What do I have to do to make it boil? And your standard answer would be increase the temperature. Get it to 100 degrees and it will boil. But 100 degrees is the boiling point of things at sea level. If you go where the air is thinner, you will find the boiling point changes. It decreases. And we're going to demonstrate that because hopefully it'd be helpful if you could actually see the thing. So I will turn that later. That would have been awkward to find out later. So you can see there the thing. You won't see it for very long, but what I'm going to do is I'm going to reduce the pressure and we'll see what happens to the water. And that is water boiling in a low pressure atmosphere. I didn't increase the temperature. All I did was remove the air that sits on top of the water that normally stops it from evaporating, from boiling, which will happen to anything. And what we'll end up with, if I go again, it's hard to see actually because it's all misted up. So we can see, let's see if we go again. There you go, let's get some more boiling. Get a lot of water evaporation onto the thing. Need to reduce the air, so we'll see something cool happen. So that was suddenly equalising the pressure. Open it up. Still got our water. We've now got a lot of water around. And there we go. That is water boiling at less than 100 degrees because you've removed the air pressure. You're removing the thing that is stopping the water molecules from escaping and going into the atmosphere, which is kind of what boiling evaporation is. We're removing them so it becomes a lot easier to escape, which means they will, and things will boil. So, final little demonstration, and this is the little alien head that our technician, Miss Birchmore, made, and what it's been filled with is shaving foam. Now, shaving foam is something that basically has loads of little air bubbles in it. And so when we remove the air pressure, when we reduce the air pressure, what will happen is those bubbles of air are going to expand and they're going to take up a greater volume. And if they take up a greater volume, well, that's going to have an impact on the shaving foam that's inside our little friend's head here. Now, because I think you may have seen this one before back in previous years. So what I'm going to do is I'm going to video this in slow motion because I think it might work better. And I'm a little bit worried about it being just being so messy to clean up afterwards. So I'm going to switch this to slow motion and then we'll see what happens as we reduce the air pressure.
That was really cool.